Showcase Summer Series here 2026, and welcome to today's webinar entitled Investigating PFAS in Canadian Water Systems. My name is Robert Nyman. I'm the Manager of Partnerships and Programs at the Ontario Water Consortium. The Ontario Water Consortium is Ontario's only sector support organization dedicated solely to water innovation. We bring together researchers, companies, municipalities, and governments to drive collaborative R&D, pilot testing, and real-world technology adoption. We help bridge the gap between research and market-ready innovation. And while there are many innovation organizations across Canada, none are focused specifically and exclusively on water like OWC does. OWC's collaborative model delivers measurable results. Over the past decade, we've helped mobilize over $90 million in project funding, supported or created more than 500 industry jobs, and advanced upwards of 80 water technology projects. We've partnered with more than 100 academic researchers and helped build infrastructure, including wastewater test beds in London and Guelph. We do this by connecting innovators with adopters and aligning the right funding, partnerships, and support to move solutions forward. Before we begin today's session, a quick note that although this is the last webinar in our Summer Innovation Showcase series, we plan to continue our Innovation Showcase webinars in fall 2026, so please watch for announcements and registration details in the coming months. All sessions are free to join. Please also note the QR code here that you can use to subscribe to the OWC newsletter. Now, I'm very pleased to introduce Dr. Scott Hawkins, who will begin today's webinar entitled Investigating PFAS in Canadian Water Systems. Dr. Hawkins will provide an overview of the collaborative research initiative and advances being made in the detection and characterization of per and polyfluoroalkyl substances, PFAS, in Canadian water systems, with a focus on improving monitoring approaches and supporting practical applications for water and wastewater treatment. Following Dr. Hawkins, we will hear from Dawson McLachlan, who will discuss non-target analysis and suspect screening of PFAS in Ontario wastewater, and Griffin Lopesack, who will present advances in gas chromatography for the non-target and trace analysis of PFAS compounds. We will also hear from Dr. Naomi Klinghoffer and Joshua Cullen, who will examine the thermochemical treatment of PFAS-contaminated biosolids and opportunities for biochar utilization, and Asan Kursedi Naslu, who will highlight integrated approaches combining membrane separation, advanced UV and VUV treatment to support closed-loop water reuse. Scott, the floor is yours.
Okay, thank you, Robert. Give me a moment to share a screen, which I believe you can see.
Yeah, we can see it.
Wonderful. So thank you again for hosting our webinar this year. And thanks for everyone who's signed on to have a listen. It is a pleasure. We're in year 4 of this project, and for those that are not directly associated with, here's our project team. So we have my group at Waterloo that focuses on analytical and physical chemistry. And on the western side of things that you'll hear from at about the halfway point, we have chemical engineering in the form of developing treatments that use pyrolysis and vacuum ultraviolet techniques. Across the board, we have participation from industry, from government and nonprofit, and from municipal partners, all of whom have been critical to the success of this project. And a big shout out to all of the people that have been associated with. I'm not going to name all the names, otherwise that's all I'll be doing for 10 minutes. So just enough to say thank you to everyone. Robert already did a good job in pointing out who's speaking, so I've highlighted those folks here. I won't talk any further about what we're going to say. You'll hear when we say it. Great. So PFAS, per and polyfluoroalkyl substances. I think everyone is now becoming very aware of what these compounds are. They're a group of man-made chemicals Many of them do not break down in the environment. There are treatment methods that are under development right now. They can move through soils, contaminate drinking water, and they bioaccumulate in fish, wildlife, and humans. So we've seen a big increase in concentration in these types of molecules over the last several years because they appear in many different consumer products, although we're starting to phase that out. And in terms of the Canadian landscape for that, Canada does not make PFAS. We import PFAS, and that's how it ends up in our environment. So when people think about PFAS, they tend to think about molecules that look like perfluorooctanoic acid. The gray balls here is a carbon chain. The sort of blue-green ones are fluorines. Those look, that molecule looks really similar to octanoic acid, which is in fact a fatty acid that you need in part of your diet. So some of the issue that we have with PFAS is that these molecules can actually mimic some of the things that your body needs, but your body doesn't know how to deal with it. And this is what causes many health concerns, things like links to cancer, thyroid issues, reproductive issues, and so on. So that's part of the reason, probably the biggest part of the reason why we're trying to get a handle on these types of molecules and how we're going to try to remove them from our environment. Now, there are lots of definitions, of course, about what PFAS are. So the EU, the European Union working definition, says that substances that contain at least one fully fluorinated methyl group, CF3, so like this guy on the end, or a fully fluorinated methylene, so CF2, would qualify as being a PFAS. But I think that that's too fine of a definition, because there are lots of medications that actually contain these groups. So things like fluoxetine, efavirenz, and I'm going to just go with Casodex for this one, are examples of these types of medicines. So I think that, you know, a finer understanding of fluorine chemistry and what a PFAS is required, so that we don't actually throw the baby out with the bathwater when we're trying to deal with these things. And I think people that suffer from depression, HIV, AIDS, and prostate cancer might actually agree with me in that space. So in terms of what we're actually doing with this NSERC Society grant that we have, for the last few years now, we've been monitoring sort of 42 of the common PFAS that we expect in the environment, now with 19 different water treatment plants and wastewater treatment plants across southern Ontario. So we've been looking at raw and finished drinking water, influent and effluent wastewater. We're now looking at biosolids, fats, oils, and greases as well, and have analyzed about 1,600 samples to date. Along with that analysis, we're developing new methods for analyzing PFAS. You'll hear about some of that coming up from Dawson and from Griffin shortly. And developing artificial intelligence stroke machine learning models for predicting properties and optimizing methods. On the western side, you'll hear about pyrolysis technologies and VUV treatment. So I will leave that to them without stealing any thunder, and just highlight some of the publications that we've had over the last couple of years talking about PFAS, new methods, analytical results in Ontario, and so on. So in terms of the timeline of the project, we're about to close year 4. And I'd say we can get maybe one more sampling round in before we have to start writing our reports and so on. So next year, this time will be sort of the closing webinar for this project. We're hoping to continue in many different aspects of this. But to give you the idea, we've sort of checked off most of these goals. For machine learning, there's sort of data is king here. So we're still collecting data in that space, but we're working towards building some really nice models there. And just to give you a visual, here's a map of the different areas that we've been testing. Blue is water treatment, red is wastewater treatment facilities. We've added a few to this, but essentially we're looking sort of Great Lakes Basin is the area that we're screening. In parallel with our PFAS work, we've been looking at some quantification of psychoactive substances and drugs of abuse. I won't talk about that here, or our non-target analysis of disinfection byproducts, but you're going to hear a little bit about non-target analysis of fluorinated species coming up. I think everyone's interested in results. So people who are at water treatment plants have seen this before. This figure is showing PFAS concentrations for a variety of different PFAS molecules in raw and finished drinking water. And the take home here is PFAS in effectively equals PFAS out. So we're not very effective in treating PFAS, unfortunately. And interestingly, we actually see some species increase in concentration during the treatment process. We're still trying to figure out why that is the case. I will note, though, the scale here, this is actually a very, very low concentration for these species. So we're actually quite safe. And if I show you what that looks like, if we sum up the 25 PFAS for Health Canada's objective, every water treatment plant that we've looked at across Ontario is in compliance. So hooray for us, we're doing a good job. We're getting close in one case. We're actually looking at some of that data right now. But I will give the caveat that if we're not removing PFAS from our environment and we're continuing to put PFAS in, over time, those bars are going to get closer and closer and closer to the Health Canada objective. So this is something that we need to keep an eye on. For completeness, here's what wastewater looks like. And it's the same story. PFAS in equals PFAS out. Note over here, our scale is 10 times larger than in the drinking water. And as we saw before, we have this molecule PFOSA that seems to appear during treatment, which is a bit concerning. So there's our bar graph showing what wastewater results look like. For the most part, we're around 70 nanograms per liter in wastewater that's coming out. If there's a higher industrial waste component to wastewater treatment plants, we tend to see a little bit higher, just to put that in context. I'll also point out, though, that particularly in wastewater, we run into challenges with interferences. So these are things that can actually give false positives and confuse measurements. And because I was asked last year about this, I decided to put a slide in this time around for a closer look at biosolids. So this bar graph is showing the concentrations in nanogram per kilogram. So this is to try to get everything on the same metric. The gray bars here are the biosolid concentrations. You cannot see the concentrations for influent and effluent because you have to zoom in order to see the like-for-like concentration in wastewater, influent, and effluent. So in other words, if we put all of these on the same scale, assuming 1 milliliter is 1 gram, the concentration in biosolids is about 1,000 times more than the concentrations that we have in wastewater, influent, and effluent, just to give you a rough number there. Okay, I think my time is coming to a close. So what's next for us? We are going to continue sampling and analyzing for the next year or so. This is across Ontario in our municipal partners and supporting R&D at Western. We're still trying to make some proposals about the origin of this PFAS that's appearing out of nowhere. And we're digging in a bit deeper in Peel region at Lauren Park water treatment plant and at the Clarkson and GE Booth wastewater treatment facilities. So stay tuned there. You are going to hear a little bit about non-targeted analysis and comprehensive screening coming up from Dawson and Griffin, who are on the line. And we are continuing our work with developing new analytical methods and multidimensional separation techniques so that we can get rid of these false positives if at all possible. So with that, I am going to turn over to Dawson, who is going to share his screen and give us an update of what he's up to.
Perfect. It's the wrong screen I am sharing. We should be all good.
Yep.
No, perfect. So, hi everybody. My name is Dawson. I'm a PhD student in Professor Scott Hopkins' group, and like he said, I'm going to be talking about non-target analysis and suspect screening of PFAS in Ontario wastewater. mainly. So I wanted to go into a little bit of detail about how we sample our water, and the main sample preparation technique we use is called solid phase extraction. So the idea is we get this little cartridge and we can pass a large volume of water through it, about 500 milliliters, but we can go lower than that, but that's around the max. And the idea is the stationary phase inside of it will trap all of our target analytes. So the chemistry in there is targeting mainly towards anionic or negatively charged species in the water. So after we have washed and then finally eluted our extract, we have effectively sampled the water, and then we can move on to our actual analysis part. And how all the data Scott was talking about is our targeted analysis. And so that is a set of 42 PFAS that we investigate specific behaviors and try to quantify each of them based off of how they behave in liquid chromatography and mass spectrometry. And this is a quantitative approach that we can take here, but it doesn't really answer the question that there are a lot of other components that we are extracting from our sample that we're not seeing within those 42 compounds. So that's sort of what non-target analysis tries to acknowledge and answer by monitoring all signals. And then you're given all of this data, and we try to piece it back together in the data processing to take a qualitative absence or presence of different species in our sample. And how we generally employ it in our lab is high resolution mass spectrometry, HRMS, which allows for a very accurate parent mass to charge to be observed. And then we can select that ion for fragmentation. So then we get its whole piece and all of the pieces that we can then assemble back to see what it was originally. Additionally, we employ chromatography, and mass spectrometry also allows us to observe some isotope ratios. So I want to flash up a little bit of high resolution data here. So on the left, we can see a parent mass to charge 263.1288, and then one at approximately a single unit larger. So this isotope ratio is around 16% and can help us assign a molecular formula. Then we can see this ion has been selected and fragmented, and we can immediately label a few of these. We can say this is a type of organic acid, but besides that, the data is quite complicated, and we have to look into it quite carefully and be able to reference match with libraries to actually be confident that we're assigning structures to what they should be. And our experimental setup is sort of already what I've discussed. We use liquid chromatography, which gives us a specific retention time. And then our high resolution mass spec on the thermochemical exactive gives us parent and product mass to charges here. With all of this data, we're then in a software called MZMine, which Griffin will also speak about later, and how he uses it for a very similar objective. But with all of this data, we're trying to answer two big goals. Can we try to screen for known PFAS using a library to basically look for specific candidates in our sample that we've measured before? But then there's a lot of data, and there's going to be additional features we haven't identified yet. So can we investigate those unknowns and assign some sort of confidence level to that identification? So to address the first goal, we can do something called suspect screening with a library match. So we've built a in-house library of approximately 100 compounds that we have their specific behavior in liquid chromatography and mass spec space. So we can rapidly screen samples for specific compounds. So for example, I'm showing one that's bis trifluoromethane sulfitamide, or triflic imide is a different name for it. But the idea is we get very accurate masses when we fragment. So there's a low ppm error is what we would call that. And then additionally, the ratios being produced are very similar as well. So we can screen and flag this compound in wastewater influent. It's present in lithium ion batteries from literature reports. And then that was sort of the screening side. If we were to address complete unknowns that we haven't measured before, we generally apply some sort of confidence level to these. So if we are confident enough to be assigning a structure, we can say level 3 is some pool of candidate structures where multiple could fit the data, and we can't say which one it is from this pool quite yet. Level 2 would be a single probable structure, but we don't have a reference standard or haven't gotten one yet, whether that's synthesis or we need to purchase one. That's sort of where you leave it with level 2. And then level 1 would be a confirmed structure that we have a reference match and we have confirmed we are seeing the exact same thing. So this is sort of in non-target analysis how we gauge how confident we are in an unknown. And I wanted to flash a few structures up and tell a little bit of a story about these. So perfluorobutane sulfonate or sulfonic acid would be a compound that we do see in wastewater influent and drinking water occasionally. And this sort of falls within our targeted method. So there is overlap between what we can see in our targeted method and our non-targeted method. And then perfluoroheptanoic acid would fall in that category as well, being within our modified version of EPA 1633. Additionally, we have that triflic imide compound. And one sort of tool we use in non-target analysis is trying to see which compounds produce similar fragments. And that can help us maybe identify new PFAS or other contaminants that haven't been identified before. And based off of that data, it showed that the compound up here, which is a dichlorinated benzoic acid, and it could be any isomer, so any movement of those chlorines or the acidic group around the benzene ring. But the idea is they do produce similar fragments, so that's why they were flagged. But you can tell they're completely different structures, and it doesn't even fall within the PFAS class. So the data analysis side is very important to be able to say confidently we're looking at something that's PFAS or not PFAS. And then the last compound within the wastewater influent I wanted to chat about is the 6,2-dipap, which we have an expanded 42 PFAS we investigate, where 8,2-dipap has 2 additional perfluoromethylenes, so those CF2 groups, so it's a little bit longer. We have screened and found the 2 shorter one in samples as well. So again, we can kind of see these class trends as well. The last thing I wanted to mention was our false positives Scott had mentioned earlier. So especially our shorter chain carboxylic acids, perfluorinated carboxylic acids, very susceptible to these. And we have signed with a reference match gamma CEHC as one for perfluoropentanoic acid. So these things behave very similarly in liquid chromatography and tandem mass spec space, and we can't differentiate them without previous knowledge or changing our methods. And in that assignment of that compound, we started at 10,500 candidate structures, and we were able to, using mass spec and liquid chromatography, as well as an additional separation dimension called ion mobility spectrometry that Griffin will speak a little bit more about later, we were able to bring that candidate pool to 1,300, and it's still very large, but we could look in literature to help identify gamma CHC was the compound we were looking for with a reference match. So that sort of concludes my story for non-target analysis today. I wanted to highlight a few points that we need to leverage, like artificial intelligence, machine learning helps us identify unknowns rapidly in the environment, as you can tell with the amount of features we're dealing with, but also the importance of a high confidence internal library to be able to rapidly screen for suspects in the environment. And both of those combined help us explore transformation products throughout the environment and treatment processes. And then Griffin will speak more about gas chromatography, which will help us explore the volatile PFAS, where liquid chromatography is very limited to your non and semi-volatile PFAS. So with that, I'd like to thank our organizers, as well as my supervisor, Professor Scott Hopkins, and our project leader right now, Amir, and the rest of the Hopkins lab and team at ICFAR, along with all of our partners for supplying samples and their support throughout the process. So thank you, and I think I'll pass it over to Griffin, who is sitting beside me.
Thank you for the introduction. Hopefully the camera will pick me up if I speak up a bit. There we go. Excellent. All right. So my presentation today will focus on gas chromatography mass spectrometry, or GCMS, for the non-target analysis of and trace analysis of PFAS in our environment. So an outline for what I'll talk about today, I'll start with a background just about some non-target analysis of PFAS in the environment, but specifically of the benefits of using GC as opposed to LC analysis. I'll talk about some of the instrumentation that I've looked at, including the ion sources that I've tried, and then I'll mention some of the ion mobility spectrometry that we've incorporated, specifically traveling wave ion mobility spectrometry, give an overview of the instrumentation, and then I'll talk about some of the method development, including library generation, the sample preparation that's specific to gas chromatography. I'll show some results, and I'll end with what our future work will be. So as has already been mentioned, PFAS stands for per in polyfluoroalkyl substances, and this is a large diverse class of compounds that are concerning due to their environmental persistence, their bioaccumulation, and that they are toxic to humans. So non-target analysis has been essential for identifying PFAS, which Dawson has touched on. But a lot of the non-target analysis, specifically towards PFAS research, has been dominated by liquid chromatography, or LCMS. And an example of this is that in 2023, papers that were published related to LC in terms of PFAS analysis were 6 times greater than that of GC analysis. So there's quite a big gap between the two. And one of the main reasons for this is that early analysis of PFAS, we were more interested in compounds that were amenable for LC analysis. So they were more polar, less volatile. And they were mainly found in or noticed in water samples, which is better suited for for LC analysis. Water is actually not a solvent that's suited for GC analysis. It can damage the column. So that's one of the reasons they gravitated toward LC. However, GC analysis can give us a good idea of all of the different compounds that are in our environment. So this is an example of the Szymanski scale. Dawson touched on levels of confidence for identifying samples via non-targeted analysis. And this is just an example where the lowest level, we have an exact match of just the mass spectrum. But as we go up to further higher levels of confidence, we get mass spec, MS2 fragments, retention times, and references to a reference standard. So for GCMS, as the name suggests, it uses gas as the mobile phase instead of liquid. So it's actually more amenable for compounds that are found in the air. So as we are finding that PFAS is not just in our water, but also in our soil and in our air, GC becomes more of an important tool for determining how much is being released into our air. GC is actually more useful for non-volatile and semi-volatile compounds compared to LC analysis. And we have to keep in mind that a lot of existing technologies, including a lot of the work that our partners at Western are doing for treating PFAS, includes pyrolysis or incineration of PFAS. And this can result in releasing a lot of the volatile compounds of PFAS into our air. So being able to monitor what is being released and how much of it is being released into our air is quite important. For GC analysis, it uses a harder ionization source compared to liquid chromatography. So for example, a lot of GC uses electron impact ionization, as opposed to liquid chromatography, which uses a softer ionization source, such as electrospray ionization. So you can see in this figure on the right here that ESI is mainly used for more polar and less volatile compounds. But if we want to get a bigger picture of the PFAS that is more volatile, GC analysis is essential for this. One thing I did notice, I started this project using a GC with electron impact ionization, and I found that it broke apart the PFAS that we were looking at into fragments that were so small we weren't able to properly identify the parent. For example, this CF3 fragment is commonly seen in almost all PFAS, and if we break apart our parent PFAS into just CF3 fragments, we can't actually figure out what PFAS we were starting with. So I found that another GC we have access to, which uses atmospheric pressure chemical ionization, or APCI, was a good sort of sweet spot in between where we were still able to visualize the parent peak, but we were also able to get some fragmentation, which helped us piece together what we were looking at. So the instrument specifically that we were using is a water synapse G2SI HDMS. And it is also capable of ion mobility spectrometry, which was useful for us because it adds another layer of identification. So traveling wave ion mobility spectrometry, or TWIMS, specifically is a gas phase technique that separates molecules based off of their collision cross-section, or their CCS. So what a CCS is it's basically the effective area that an ion interacts with a buffer gas. And it can separate molecules because as it travels through that buffer gas, the larger the analyte, the more it will interact with those atoms in the buffer gas, and it'll kind of be dragged back, where the smaller the analytes will ride that wave easier and elute from the twin cell first. So you get separation based off of that, and it's proportional to, again, its collision cross-section, which is very specific to its shape and conformation. So if we were to, so when we build a calibration curve based off of a set of compounds of known collision cross-sections, and we measure their drift times, or the amount of time it takes to exit the twin cell, we can create a calibration curve where if we measure the drift time of an analyte, we can get its collision cross-section, and that tells us a lot of information about its shape and conformation. This specific instrument is also able to use MS2 experiments. So typically, a conventional MS2 experiment will involve a triple quad. So you have the first quadrupole, which will select your parent ion, the second quadrupole, which will fragment it, and then the third quadrupole will scan for the fragments. And you can use those fragments to sort of reverse engineer what PFAS you started with. So this instrument is also capable of this, though it doesn't have a quadrupole. It has a trap here that guides the ions into the twin cell, and this can act as a collision-induced dissociation cell to get our fragments. So if we look at the overview of our instrumentation, we can inject our sample into the gas chromatography, which gives us our retention time. It goes into our APCI source, which maintains our parent ions and gives us our MS spectrum. It enters into the trap and gives us our fragments, or our MS2 fragments, and both of these enter into our twin cells, where we can get our drift time and therefore our collision cross-section. So the method development for this, specifically the library generation, involved collecting the retention times, the mass spec, the MS2 fragments, and the collision cross-sections for all the standards that we had available. And then we compiled them in MZMine, or the software MZMine, which allowed us to create a library that we could use to scan our unknown environmental samples. These samples first have to be prepared with solid phase extraction, which Dawson talked about. But specific to gas chromatography is we need to derivatize our samples as well. So for gas chromatography, as I mentioned before, our analytes need to be sufficiently volatile, and sometimes they're not. So in order to make them volatile enough to visualize in the GC, we have to derivatize them. There are different methods to do this, but the one I chose is an acetylation reaction, which takes hydroxyl groups, or OH groups, and we treat them with acetic anhydride and a base, in this case pyridine, and we create we acetylate them so that they're more volatile and therefore visible in the GC analysis. So here are some of the results that I have so far. I've looked at hydrolyzed at 675, 600, and 500 degrees Celsius by Josh from Western. And I'm comparing them to an SPE and extract blank as well. So whenever we do SPE or an extraction of our samples, we like to run a blank to make sure we're not getting any PFAS contamination or losing any PFAS as well, which we determine by spiking these with internal and external standards. So you'll notice these first 10 peaks here are present in all of the samples, including the blanks. These are our identified internal and external standards. So this tells us we're not losing our PFAS in our extraction processes, and it tells us that our library matching workflow is working. So those are 2 pluses. So if we look back, we can ignore sort of the first 10 peaks in the chromatogram for our samples. And if we focus in on the peaks that we don't see in the blanks, we can see two main ones at retention time 963 and 1193. Now, I'm still working on building my library, so we haven't gotten a hit quite yet for the retention time at 1191, but we do have a hit for the peak we see at retention time 9.63, which is highest at the 500 degree biochar. 500 degree biochar. So if you look at the data results on the column on the left, you can see that the mass spec parent peak is 463.01468, which is very close to the library match of 463.192. The MS2 results I'm still collecting because it takes some time to go through. So we don't have the MS2 results completely, but we do have the retention time match, and we have a collision cross-section match within 2% air. So that's 3 out of 4 of our identifying factors, which gives us a very strong tentative hit for our 1H, 1H, 10H, 10H, perfluoro 110 decanidiol. It's a very easy compound to say. So this gives us a good proof of concept that our library matching and our workflow for GC analysis is working. It is quite a bit behind LC analysis, so it's taking some time to get the same kind of results and build the same kind of library. Future work will consist of continuing our analysis of biochar extracts, and I'd like to begin quantitative analysis as well involve building some calibration curves. We'd like to also develop the workflow analysis to look at some oils and gas samples right now. They're quite dirty, those samples, so they can be damaging to the machine if we aren't careful in sample preparation for those. And we'd like to expand on the current PFAS library as well as complete the MS2 scans that we're adding to our library right now. So I'll end there with acknowledgements to everybody who set up this webinar today, as well as all of our industry partners and the municipalities that have been generous enough to work with us. And I'd like to also thank the Hopkins, Broody, and the Klinghoffer Labs as well.
Joe, I think we're turning over to Naomi now, if I remember our schedule correctly.
Yes, thank you. Is my screen visible?
Yeah.
Yep.
See ya.
Yeah, okay, great. Thank you so much. Thank you all for the opportunity to talk today. I'm Naomi Klinghoffer, and together with Franco Baruti, I am leading the work here at Western. And as was mentioned, we focus here on developing technologies for treating and destroying PFAS in Canadian water systems. So today you'll hear from me as well as our two PhD students, Ehsan and Josh, and we'll also see some of the work that's done by our postdoc, Neha. So the work we do here is conducted at ICFAR. This is our Institute for Chemicals and Fuels from Alternative Resources. So this is part of Western University, and these are our labs. You can see our facility here. And we're an off-campus research facility with some ability to make larger scale reactor systems. So here we build customized pilot plant reactors at industrially relevant scales. You can see some of them here. The idea is that as we develop technologies, we like to scale them up. We like to demonstrate their feasibility. And then we also have analytical labs on site so that we can analyze our products, characterize our feedstocks, and understand and improve the processes that we are designing. To kind of highlight our collaboration with Scott Hopkins' group at Waterloo, we run the pilot plants here at Western, as I said, and then we send Scott all of our samples. So, you know, when we do our degradation processes, we then send the treated water as well as our biosolids, biochar, and bio-oil products and the sampling media over to Waterloo, where they analyze the PFAS for us. To highlight a couple of the projects here at Western that you're going to be hearing more about with the subsequent speakers. First, we have the project by Ehsan, who is working on developing an integrated process for separation and destruction of PFAS in water. This process uses a membrane as well as a VUV water treatment system. And then our other technology for PFAS destruction focuses on thermal treatment. So in this process, we're using pyrolysis, and we're specifically applying it to biosolids from wastewater treatment plants. As Scott had mentioned earlier, the biosolids contain very high concentrations of PFAS, and so we want to develop technologies to actually remove and destroy the PFAS from that specific medium. So what we do here, our approach to PFAS destruction in biosolids is using pyrolysis as a thermal treatment. The process flow is that we receive the wet biosolids from a wastewater treatment process. We'll then dry it in-house to a moisture content that is acceptable to feed into our pyrolysis process. In some cases, we'll spike the biosolids. So in certain examples, we want to look at the impacts of higher concentrations of PFAS. We can choose specific PFAS to spike with if we would like, and it can also make it easier to track the flow of fluorine. However, we also run many cases with the biosolids as received without any spiking. We then recover the biochar from the process as well as the oils and gases. And with each of these steps, we are measuring the PFAS in those products or process feeds. Our system is also equipped with a gas emission train sampling system. So for this, we are using the OTM 45 and 50 sampling processes in order to recover any PFAS that's coming out of our process in the gas or vapor phases. We receive biosolids from a number of different locations across Ontario and in the United States. And these biosolids come from wastewater treatment plants with different processes for how they treat the wastewater. So this gives us some sort of variety in terms of the properties of the biosolids that we receive. We can then characterize them here at ICFAR in terms of their sort of bulk and surface properties, and then send them to Waterloo for the PFAS quantification. To give you an idea of some of what we have received, this shows the concentration of PFAS in biosolids from 5 different wastewater treatment plants. Of course, they're not identified here, but what we can see is there's quite a range in terms of the PFAS concentration. And in Ontario, much of the biosolids are used for land applications. So it's really important that we make sure that we are not, in fact, putting that PFAS back into the soil. Currently, there's a 50 micrograms per kilogram PFAS limit. And we can see that there's a good chance that we may be exceeding that in certain cases. And this is the motivation for developing this technology for removing the PFAS from the biosolids. The technology that we use is pyrolysis. This is a process where we heat something up in the absence of oxygen. So unlike traditional combustion where you have oxygen and you produce gas, carbon dioxide, and water at the end, we're actually producing a few different product streams from this pyrolysis process. We make a gas stream, which can be used typically for energy recovery. We make a liquid stream called bio-oil, which is conventionally used for energy or chemical production. And then we make a solid stream, which is called biochar, that can be used in industrial and agricultural applications. In our treatment process for biosolids, we are feeding biosolids into our pyrolysis reactor and producing these 3 product streams. The gas and the vapor phase, or the bio-oil, we then further process in a thermal oxidation step, which is happening at temperatures around 1,000 degrees Celsius. In this way, we can ensure that we have PFAS destruction at this very high temperature without having to burn all of the biosolids in our process. So we're also then producing biochar, a solid residue, which we're evaluating for waste treatment applications. We've seen that we've achieved almost 99% or above 99% removal of PFAS in our biochar, meaning that through this pyrolysis process, we displace the PFAS from the solid into the vapor and gas phase, and then we can go through that destruction process in the vapor and gas phase and retain the biochar for other applications. Biochar has many different applications. It can be used in soil amendment, water filtration. The carbon is very stable, so it can be considered a carbon sequestration pathway, incorporated into materials, etc. So there's a way that we can use this to promote a circular economy by utilizing the products while still destroying PFAS. One of the applications that we're looking at for the biochar is using it for stormwater remediation. The idea here is we're taking the biochar and we're using it to remove nutrients or organics or inorganics from a stormwater treatment. So we've built columns here at ICFAR. We're using real stormwater that we collect from rain events. And then we're characterizing the biochar before and after. We expose it to stormwater. We have a continuous flow system, and then analyzing the water that comes out. This is a new process that we're working on, so we don't yet have results. It's running as we speak. But this is what our columns look like. And you can sort of see how we have these different layers with the biochar right there in the middle. We're testing and comparing a number of different mediums. So we have our biosolids-derived biochar, as well as poplar-derived biochar that's in 2 different forms. This is kind of a highly engineered biochar, which we're comparing, as well as our positive control, granular activated carbon, and a sand bed as a negative control. Another aspect that we're looking at is the idea of using biochar to potentially remove PFAS from water systems. We've done a lot of work where the biochar is a medium where we can engineer the surface properties of it. We can add functional groups, we can change its surface structure in order to make it specifically targeted for removing specific pollutants from wastewater. So we've looked at pharmaceuticals, dyes, and in the future, we're going to be looking at engineering biochar for PFAS removal. So with that, I'm going to pass it on to the other ICFAR members who are going to show you some of the results from our pyrolysis as well as the membrane and VUV treatments. Thank you.
Okay. I just get a thumbs up, Naomi, if you can see that. Okay, perfect. Okay, good afternoon, everyone. My name is Josh. I'm a PhD candidate working under Dr. Brooding, Dr. Klinghoffer over here at Western. And today I would like to talk to you all about our project that has been focused on treating PFAS in biosolids. I would like to give a summary of our main pilot system, explain our treatment approach for PFAS, and give an overview of our workflow with some research updates. And along the way, I would like to also add some comments about what work we're looking at doing in the near future. So from the outset of this project, we've been looking at how we can process biosolids with our pyrolysis and combustion system. The main idea being that we can first pyrolyze the biosolids to displace PFAS from the usable biochar. We then combust the vapors and gases to provide energy back to the system, while also breaking down the displaced PFAS. And so with this system, what we are trying to do is improve how we are able to track PFAS within each stage of the treatment process. That's really been the main goal. And so the idea for this approach traditionally has been to control specific parameters like reactor temperatures and solid and gas residence times to ultimately achieve some degree of fragmentation of the longer chain PFAS molecules, which could also potentially result in some transformation into other forms. And so the focus for us has been to better characterize the outputs of this treatment by implementing some more advanced PFAS and PFAS byproduct sampling methods. We've also been exploring a possible third avenue of transformation, which is using calcium. So for example, calcium minerals such as calcium oxide and calcium hydroxide to react with the available fluorine and form a stable, relatively inert calcium fluoride mineral rather than having a volatile form of fluorine in the emissions. So we have really been putting a lot of focus on how we can better track PFAS within our workflow. I have here a graph not specific to any data set, so the actual results are just values I chose for today. But I just wanted to illustrate how we're aiming to map it all out for each stage of our treatment process, that being the drying, pyrolysis, and combustion with metal capture being added in. The core idea for how we are approaching this is to not only improve how we are measuring what the volatile fragments could be, we are attempting to integrate metal minerals with calcium that can react and trap the available fluorine into a stable form. And so we also have been looking at how we can maximize the capture of PFAS with metals within the system, hopefully reducing what PFAS remain, if any, in the char from pyrolysis, and then also the volatile forms or PFAS in the flue gas from combustion. So that has been our general approach, and I've broken our research updates into a few stages based on how we receive and process samples. So firstly, we have received samples from several wastewater treatment plants ranging from 20 to 75% moisture. And in order to feed these samples into our systems, we need to first reduce the total moisture to roughly 10 weight%. So we've been doing bulk drying of the material in tray dryers, reducing the moisture content, and then also reducing the average particle size, so it's better to feed into our system. And what has been key with our collaboration with Waterloo is that we are able to track specific PFAS through these various stages. So here is a bar graph of the wet and dry samples from five different wastewater treatment plants, showing micrograms of PFAS per kilogram of biosolids on a dry basis. And I've separated out all the PFAS into five main groups. But the main thing I want to point out is that, like other recent studies for drying of biosolids, after drying, we see a considerable loss even before we begin treating the sample in our system. So I have it here organized based on moisture content that we've received, with the drier sample showing lower losses and the higher moisture content sample showing much higher losses. So this was initially just more of a supplementary data set for our project because we just had to dry the material in order to process it. But because of the significant losses, we have expanded this part of the project into our recent work by replicating the drying, our bulk drying, into a smaller closed system. So because our tray dryer does not actually capture any of the moisture, we only looked at the solids before and after. We adapted a rotary evaporator system to replicate our bulk drying conditions for drying, or bulk drying conditions. And so with this system, we can load the wet biosolids in, and then after drying, take samples of the dry solids that are left, collect the condensate that is condensed from the condenser, and then also rinse all of the surrounding glassware surfaces. And with this, we can analyze each phase using target analysis to determine whether PFAS are truly displaced or there's some kind of transformation occurring while drying. So this will give us a much better idea of what's actually going on during the drying process. So after drying, we then pyrolyze the material, producing a biochar and then the vapors as well that we can analyze. So in the past, we had done extensive work looking at different conditions for pyrolysis to remove high amounts of PFAS from the solids. And we've been building on this more recently, focusing on PFAS spiking and then also evaluating the effectiveness of calcium loading for fluorine retention. And so from this initial testing, we looked at running the lowest temperature and residence times for biosolids spiked with PFOA and small loadings of calcium. Fed and pyrolyzed material at 500 degrees, removed the char, so there was a residence time with 15 minutes. And then we condensed the vapors and sent all the samples of the the outputs to Waterloo for analysis. And so from analyzing the products of the system and comparing the total PFAS measured on this bar graph, a spiked sample with no calcium added compared to spiked samples with calcium added 5 and 10 weight%, we can see that the addition of calcium illustrates a significant reduction in measurable PFAS within the product streams. And based on this reduction, we can anticipate that the added calcium is suppressing the release of volatile PFAS by reacting and securing fluorine as that solid mineral I was talking about before, calcium fluoride. However, we want to do more work to confirm this, repeating some tests and utilizing some different methods to actually verify the presence of these minerals within the char. And lastly, what I also want to talk about today is the work where we've been combining all the stages of our process to run longer tests, receiving larger samples of wet biosolids, drying, and going through the full process of pyrolyzing, combusting, and the emission sampling for the flue gas. We've been receiving larger samples of wet biosolids, which we have done testing spiked and unspiked with PFAS. We pyrolyze the material to make the biochar while also combusting the vapors to further treat the volatile fluorine, sampling at each stage for target analysis along the process chain. And finally, we do emission sampling for the flue gas using the OTM 45 and 50 standards by the US EPA. So OTM 45 uses a series of filters and absorbents to collect and isolate PFAS remaining within the flue gas, so heated filters, absorbents, impingers. And OTM50 is a canister method to collect a sample of the gas for a list of possible fragments that the PFAS could ultimately form after combustion or as a result of combustion. And at this stage, we finished 2 sets of tests for this, and we are currently working on a larger third set for the next few months. But to kind of sum up all the stages, this will give us a better idea for how we can track PFAS at each stage, drying, pyrolysis, and then also now combustion for volatile fluorine in the emissions. And so before I pass it on to Ehsan, I would like to especially thank our collaborative team at Waterloo for all the help they've given us over the years, especially Amir. And I would also like to thank you all for your time, the other collaborators on this project, and the other supporters for this project. So thank you. And I'll pass it on to Ehsan.
Okay, hello everyone. I'm Ehsan, PhD candidate at Western University, and I'm working on developing a new configuration based on integration of the separation and destruction to address trace organics like PFAS. So just before start, I believe anyone who participate in this webinar knows about the importance of the water reuse. But if you want to go through that approaches like one water approach, one of the main challenges you will face is compounds of emerging concerns like pharmaceuticals, like PFAS. So if you want to address them with the conventional water and wastewater treatment, they are either insufficient or useless to completely remove the risk of these organics. So we have to go through the advanced treatment systems and may apply some process intensification to increase our efficiency and effectiveness of our treatment system. So what we are doing is the integration of the high pressure membrane, and in this system, I mean vacuum ultraviolet, which you can maybe in the future you can exchange it with any kind of degradation that you have in mind, to trap the chemicals, the forever chemicals in this case, or any organics inside a closed loop system. But I have to clarify here that the idea is not just putting a VUV after RO or NF, it's just to some concentrate treatment. The main idea is to use the membrane fractionation, what membrane can select for us as some sort of a treatment domain that we can send it to the VUV, and doing this over and over to make sure that we can remove the chemicals completely. So if you go through the see these techniques, I mean, separately, and isolate them and see what they can bring for us and what's the problem they have. We can say it like in a simple words, if you use a high pressure membrane, you can protect the permeate. But on the other hand, you have to deal with the concentrate. Or if you go through the using AOP with the vacuum ultraviolet or UV hydrogen peroxide, you can transform persistent chemicals. But on the other hand, the available dose that you can bring to your target chemicals is highly dependent of the matrix that you are dealing with. So the question that we had was, what if the membrane selected fraction as a waste does not become a waste, but become a reactive domain that we can send it to VUV over and over in a steady state water matrix. So based on that, we built this pilot which is right now running at ICFAR at Western. So it has a tank, which goes the water pumped through the membrane, the permeate, the clean water leaves our control volume. The concentrate goes to the degradation unit. The outlet, after a small bleed, recirculate back to the tank. So that bleed is so important for us. So imagine without that, we are just concentrating everything, all the inorganics and organics that membrane can fractionate and we cannot transform it inside the tank. So exponentially, it's going to be increased till we fail the membrane. But with this bleed point, we believe mathematically there is a steady state that we can reach to that and run the system on that level. So, but because we are recirculating back, so we can have some sort of accumulation of the constituents inside the system. So we introduced the accumulation factor, but then we realized there is two types of accumulation factor that we have to deal with it. One is the water molecules. So this formula is just for the hydraulic accumulation factor. It says whatever stays inside the system to whatever leaves the system. So this is completely hydraulic. So just in order to give you some insights to understand this better, for our pilot, this number is around 5 to 10. So it says that the water molecule has 5 to 10 cycles before leave the system. But on the other hand, we understand we have a water constituent accumulation factor. This is completely important and different than the hydraulic because it depends on the rejection efficiency in the membrane. So imagine we have two compounds, one with 99% rejection in membrane. In that case, you can get over 100 cycles inside this loop. Or if you have 95% rejection with just 4% lower than the compound A, you can get around 60 cycles before that compound either leaves through the membrane or through the bleed. But this accumulation factor has another meaning for us as well, because we have a VUV inside this loop. So we can translate it to dose. So for a single pass, you get one pass through the VUV and one dose. A hydraulic and water molecules get 5, but the species-specific accumulation factor, you can get either 20 to 150, which dictates by the membrane rejection and the amount that you bleed from here. If I want to make it more, understandable, we have the NDMA as a compound for probe UV that people use to understand the fluence of the lamp or the power that they can get to the system. So for this, based on the literature, for 1 log degradation of NDMA, you need 1,000 millijoule per centimeter square. But if you can trap the NDMA for 100 cycles inside this loop, you just need 10 millijoule. And if you can deliver more than that, NDMA never sees 100 cycles. So based on this understanding, we start the first phase, which was the proof of the concept. So our main question was that the membrane and the VUV, are they, can we run them together? Is there any synergetic effect between them? Can they benefit each other? So we chose 4 pharmaceuticals and we designed our pilot, which has a 900 liters water in 3 modes: just separation with membrane, just degradation, and separation degradation integrated. And we compared the quality of the permeate, the product, whatever left at the treatment as a retentate or concentrate, and finally, degradation efficiency. And plus, we compared the EO of these treatments. In all of these 4 comparisons, the integrated system was better than the other to solve separation and degradation, which was understandable because membrane concentrate pharmaceuticals before sending to VUV, and VUV in each cycle remove part, which helps membrane to protect our permeate. But here I want to show the EO graph, which is very exciting. This system, the integrated system, has a high pressure membrane, which costs lots of energy for us. But the EO of the integrated system was much lower than the just degradation, which has no high pressure pump, because of the high kinetic that you can get, faster kinetic that you can get in the integrated system. And also for the hard to treat chemicals like caffeine, this difference is much more visible because we can get faster kinetics in the integrated system. So the next step was to see, as I said, with that bleed, we should reach to the steady state. Mathematically, yes, if you solve the ODE of this system with this control volume, definitely you can reach for that. But what about in a real pilot that we have? So we chose conductivity as an inert probe compound for us, which has no transformation in VUV, so we can track it easily. And we chose 4 bleed flows, like from 0.2 to 1.6 liter per minute. These numbers for themselves has no meaning, and but I can translate it in a better way. Bleed 0.2, which is so small, it means that we have higher accumulation factor inside the system. And because of that, we reach to the steady state late and in a higher levels. I mean, we start with water with 300 conductivity and we reach to around 3,600 conductivity. And when you choose bleed 1.6, which is a high bleed, it means that you are wasting too much and you have a lower accumulation factor. But on the other hand, you reach the steady state faster, and the water matrix that you are going to have in a steady state is much more cleaner than lower bleed. So this can be a issue with the scavengers and other stuff that you may be accumulating inside that water. So by knowing that, the other thing that we understand through these experiments, that we don't have one steady state. I mean, I cannot say that this pilot with this bleed point, you have the steady state level of X. No, each constituent has their own fate inside the system. So we realize, for example, here you can see the graph of the sulfate and chloride. So the chloride reached the steady state faster, and in the level of 18 milligram per liter. Sulfate reached to steady state even close to 120 hours, and which is around 7 milligram per liter. So this shows that each of these compounds have their own story inside this closed loop that we made, and shows us one of the things that we can buy through this closed loop. One of the things that I mentioned was the dose amplification. The other thing that we can buy is tailoring the water matrix, because when you are concentrating the sulfate inside your system, or chloride, you may have opened a new degradation pathways to your system, because each of them can have, especially in the VUV systems, which you have 185 nanometers, you have new radicals that can help to degradation of your organics that you have inside the system. But we should be a little bit careful here. We are not just concentrating chloride and sulfate, we are concentrating total organic carbon as well. So there's definitely a sweet spot that we should find, that between the water matrix that we are tailoring and the accumulation factor that we can get. But after we realizing that each constituent has its own story, we realize we cannot predict the system without a good model. So we made a model based on differential and algebraic equations, which you can see here just 4 equations, but it has more than 200 equations and variables. And as a first step, again, let's see how the hydraulic works with our inert probe, the conductivity. And as you can see, we capture the trend perfectly, and the RMS is so small. Just to mention one small thing here, that because we have a inline sensors, our experimental data look like a model, but because we have data every 10 seconds. So the other thing that we, try to investigate is that the different degradation pathway that we can get through the VUV. We have direct UV, which is by 254 nanometer, and we have degradation through the hydroxyl radicals and hydrated electrons. I can finish it in one or 2 minutes. Yeah, it's okay. And for that, we chose 2 probe compounds. One is PCBA, then the other one MCAA. And we try to see the degradation pathway that we can get through these probe compounds. And as you can see here, this is a continuous running. This is not a batch test in a lab scale. This is a 900-liter tank, which is continuously feeding with the PCBA and MCA for 120 hours. And we could capture the trend through this our model, and through this data, we could update our model to have the hydroxyl radical degradation and hydrated electron degradation. Even you can see here, we have the whole scavengers as well through the contribution to OH sync throughout the whole 120 hours, because our model sees each constituents individually. And just to wrap it up, so we had bench scale VUV degradation that shows that the PFAS can be degraded by VUV, and also lots of other articles that support this claim. And also we have non-targeted analysis that shows we have this lots of small branches of PFAS growing through the VUV degradation. But we believe through this closed steady state closed loop, we can amplify the dose, we can reduce the DO automatically because we are increasing the organics inside the system, and the oxygen drop automatically, and we can tailor the water matrix based on the bleed point that we are choosing. And finally, you can see here our close partners that through the Waterloo and also the Brown and Caldwell and USB Technologies. And I would like to thank everyone that's helping us to do this research. Thank you so much.
Great. Thank you very much, Ehsan, for concluding the presentation, and thank you to the teams at the University of Waterloo and Western University for the update on the project. That was great. We'll now move into the Q&A and discussion section for the last 15 minutes or so. Just before I do that, I'm just putting in a link in the chat here for those who are attending and are perhaps not aware of an event coming up next week related to PFAS management, entitled Governance and Technical Strategies for PFAS Management Symposium. This is a symposium being hosted in partnership with the Toronto Metropolitan University and the Ontario Water Consortium as well on June 16th. That's next Tuesday from 9 to 4 p.m. It is in person. There's a registration link here if you're interested in learning more. But yeah, let's move into the Q&A section. You're welcome to pose your questions using the Q&A function, or you can drop them more in the chat, or alternatively, you can raise your hand and I can unmute you and you can speak directly to whoever you want to ask a question. But I'll give everybody a little bit of time to pose your questions and then we'll get started. I do see a question already in the Q&A section by Mark Payne, and this question is directed at Naomi. And Mark says, Naomi, in your last slide, I think you said something to the effect, pyrolysis removes PFAS from biochar. Did you mean removes PFAS from biosolids, or did you mean biochar?
Yeah, so I'll clarify what I guess what I meant. So the biochar is the pyrolysis product. It's the solid product that we get. So what I was saying there was that, when we treat the biosolids through pyrolysis, we end up with a biochar that is effectively PFAS free.
Thank you, Naomi. All right. And again, you have an opportunity to ask any questions or make any comments in either the chat function, the Q&A function, or by raising your hand. Everybody a few minutes to get their thoughts collected. All right, we have a new question in the Q&A section by Sonia Clayweg. Could you comment on the number and types of biosolids that exceeded the CFIA standard for PFAS? I'm not sure who that was directly addressed to, so perhaps I'll let Scott answer that.
Yeah, I can answer. The number I'm not 100% clear on. This will be through Josh, but I would say the fraction is quite high. Typically, we're above the 50 microgram per kilogram level. What we've measured in Ontario is pretty close or below that. I think it's more the American ones that tend to be higher, if I'm not mistaken. Josh, can you back me up on that? Or not?
Yeah, that's essentially, yeah. Right.
Yeah, without putting any names on any of these places where we've gotten biosolids from, of course.
Okay, thank you. And there is actually another question directed at you, Scott, from Tim Fletcher. Scott, in your sums of PFAS for drinking water, did you only report levels over the detection limit? Did you include any values for PFAS smaller than DL, i.e. HC practices taking these as 0?
We're only reporting things over quantitation limit. We're not reporting anything below quantitation. So if we're between detection and quantitation, we don't report. If we're below detection, we just say we're below detection. We don't put a number on it at all.
Perfect. Thank you, Scott.
Trying to be careful.
There's a new question in the Q&A section. Is there an appetite for field deployable rapid sensors for PFAS monitoring, trade-off a degree of accuracy / sensitivity for increased data? This is from Shadman Khan.
I would say that there is an appetite if you can develop a rapid sensor for PFAS. It's very difficult because the concentrations are typically quite low. There are field deployable solutions. In fact, we're developing some in our lab right now so that we can do passive sampling. This is in partnership with the Ministry of the Environment, Conservation and Parks. So we have some of these out on campus here in Waterloo right now to test our own environment first and make sure that we're getting good results before it goes out into the real world. The technology, though, relies on us deploying for a while, collecting, and then analyzing in lab after the fact. So it is actually a pretty involved process, but that's what you need to do if you're going to get accurate numbers currently. That helps.
Thanks, Scott. All right, once again, if you have questions or comments, you can place those in the Q&A section, the chat, or you can raise your hand and I can unmute you. Scott has his hand up. Go ahead.
I have a question for Naomi, now that I think of it. How involved is it to tailor your biochar so that you're selective for particular micropollutants?
There are a number of different processes. So some of them are, treating it with something like an acid or hydrogen peroxide. Some of them are treatments in, CO2. Some of them are thermal treatments. So it's not a terribly complicated process. If you're doing washing with liquids, it can get into, large volumes that you're handling at scale. But the process itself is fairly straightforward and scalable. So it's something that I think there's a lot of potential there. And we've done a lot with showing how we can target it for specific pharmaceuticals. So I think it's a matter of just figuring out what's the formula for PFAS.
Thank you. I should have asked that before in one of our group meetings, but there we go.
I did just see a comment question that was attached to Mark Payne's original question that just came in by Michael Sasjes. Sorry if I mispronounced that. In the VUV treatment loop, are you also looking at pH adjustment or electron donors, or is there an issue with accumulation by the membrane? So yeah, that would be perhaps for Ehsan.
Oh, yeah. I am happy for that question because I lost a little bit of time. So I can use this opportunity to show some of my more data that I have. So the pH, we have adjustment of the pH again automatically. I mean, it's a little bit exciting till today what we got, and we tested by PCBA and MCAA and NDMA till today how our system works in this closed loop, which also we have a product as a permeate. And we realized this concentrating of the water matrix, in some cases also it helps. I mean, more helpful for us, like this is the DO graph, which I missed to show. It doesn't matter which bleed point you choose, the DO drops itself, which opened the redox window for us without any. So you know that people, in order to have in the ARP, people add sulfite to get rid of the oxygen. So imagine if you want to continuously run the system for just contaminated groundwater, how much sulfite you're going to add to your system. But in our system, because of this concentration of the organics, the DO drops itself below 1 milligram per liter. This also applies to the pH. Not that much that I can show it like here, but the pH also gets more to the basic side, which is also good for AOP, and adjusts automatically itself. And I can say more or less our pH is close to 9, which is concentrating to organic. But again, this all of this depends on the water that we started with, which is a treated groundwater that we have, on-site treated of groundwater of the ICFR that we have. So I don't know, maybe definitely, I mean, in different water matrices, we will see different changes inside the water, but this is what we have till today.
Great, thank you, Ehsan. All right, I don't see any further questions right now. So we are in the last 5 minutes that are available to the audience to ask questions. So please, if you do have questions, ask them or comments, please let us know in the Q&A section, the chat, or raise your hand and I'll unmute you. Okay, I don't see anything more coming in. Oh, one more just came in by Justin Wong for Scott. There was a mention of interferences in wastewater and biosolids testing. Is there a specific reason that this applies for short chain compounds? Is this issue prevalent in standard, in brackets, commercial lab testing?
Yeah, so in reverse order, yes, it's prevalent in commercial lab testing, whether they realize it or not. I won't comment on because I'm not sure how they would deal with that commercially. The reason why we see the short chain species being interfered with is because fluorine is quite heavy. So if you have 20 fluorine atoms in your molecule, then you end up with a much heavier molecule, and then you tend to have that pushed out further in the mass spectrum. Whereas for the smaller fluorine species that are lighter, those overlap with the common organic and biomolecular species that you would see in wastewater. So you have much higher chance of interference when you're at lower masses. So the short chain species are notoriously difficult to analyze because of that. But the flip side is they tend to be in higher concentration. So then you sort of get away with analyzing them because the interference is often a smaller portion of the total signal that you're observing. In our case, looking at perfluorobutanoic acid and pentanoic acid, those are sort of in a weird region where the concentrations are low and the relative intensity of the interference is high. So then it becomes challenging to actually quantify those rigorously, we'll say, without more substantial effort being put into the analysis, which is what we're doing. So good for us.
Thanks, Scott. Maybe time for one more short question in the next minute. If there's a quick one coming in, give everybody maybe 30 more seconds. If not, we'll wrap up.
Okay, I just saw a comment from Mark Payne asking if it's 6.2 FTS driving the levels in drinking water's gray box. So I need to open my presentation again and have a look. I can bring that up. Drinking water.
We have Mark putting up his hand. I'm going to allow your mic, Mark. You should be able to unmute yourself and speak.
Yeah.
Now, Mark?
I was just wondering because there's, I think, 2 gray boxes with it 6.2 FTS it's driving, especially in that water treatment plant number 5. Or was it one of the, or is it the lighter gray, which is that PFHXA?
It's the 6.2 FTS, I think, is the major one that's driving that one. So yeah, it's hard to tell. Unfortunately, we don't have enough colors in order to handle all of these. Yeah, 6.2 FTS is usually the bigger one, but we do see the hexanoic acid as well as being a contributor for most of these. Slightly different grays. The lighter one is the 6.2 FTS.
Okay, thank you.
Yeah.
Okay, great. That concludes our time, and that concludes the webinar. I want to thank all of the presenters, Scott's team, Naomi's team, obviously Dr. Franco Baruti, who was unable to be here today too, but thank you to all the presenters for the update on the project, Investigating PFAS in Canadian water systems. I hope everybody enjoyed. We look forward to the final update, at least of this portion of the project, next year, and to any future initiatives related to this. But for now, again, thank you to everybody, and thank you to the audience for being here and engaging. And we hope that you have a great rest of your afternoon. Thank you.
Thanks, everyone. Thanks, Robert.